Hello guys and welcome back to my channel Interview with Bunny, and today we will be discussing another important question on system designing, and the topic or the application that we will be designing today is considered as one of the important questions for the technical interview, and that is the designing of a ride booking application such as Uber or Ola. So since you guys are already familiar with this type of application, so without wasting much time, let's get started with the first step of our system designing, and that is gathering of the functional requirement. But before starting this video, I would highly recommend you to go through the 7th video of this playlist, because over there I have discussed the proximity search in details, and the concept of the proximity search is very much needed when you are designing any application like this. So with the assumption that you have already covered the 7th video of my system designing playlist, let's move forward. So the first step of our designing is gathering of the functional requirement. And the functional requirement of this system is quite simple and straightforward. Number 1, user would be able to get a fair estimation after giving the start and the drop location of a particular ride. Number 2, after getting the estimation, the rider should be able to request for a ride based on that estimated value, and he should be able to request for different type of vehicle. Means when we are giving our estimation, we should give the estimation for a car, for a bike, for a SUV and all those things. So based on the different fare estimation that we are giving on the front end, the user should be able to select and request for a ride on that category. Number 3, the rider should be matched with a nearby available driver. Number 4, on the driver's end, driver should be able to accept or deny a particular request based on the drop location or the estimated fare. Number 5, both the rider as well as the driver should be able to track each of them on near real time. And number 6, at the end of the particular trip, the rider as well as the driver should be able to provide rating for each other. And the last but not the least, with the help of our application, the rider should be able to pay the last and the final amount to the driver. So these are more or less all the 6 functional requirements that we have to solve with our designing. So let's list down all these functional requirements over here. So these are all the functional requirements that we will be solving over here in this problem. Now since we are done with the functional requirement, let's see what will be the non-functional requirement that we have to solve. So let's list down all the non-functional requirements over here. So the first non-functional requirement that we have to point is the scale of the system. So once you ask your interviewer that what is the scale of the system that you are designing for, your interviewer will tell you that we are estimating millions of user and driver across our application. So you can easily understand that the scale of this application is quite huge, and based on that we have to design accordingly. So here the first non-functional requirement would be the scale of our system. And the scale that we are targeting over here are the millions of the users and the drivers across our application. Now the next most important non-functional requirement is the cap theorem. And as you know, the cap theorem tells that whenever you are designing a distributed architecture or a distributed system, you either have to compromise between the high consistency or high availability of the system. A single module of your application cannot achieve both high consistency as well as high availability in a particular module. So here if you understand our application should be highly available for the user. Means once the user is looking for a trip in our application, then our application should be highly available, because if our application is down, the user won't be able to book a ride. So from the user aspect, the application should be highly available. But on the flip side, from the driver aspect, the system should be highly consistent, so that a particular driver is not mapped or assigned to multiple users at the same time. So here what we will write, based on the cap theorem, that the overall application with respect to the user should be highly available, but with respect to the driver, means when we are assigning a ride to a driver, then it should be highly consistent. So here you can see it is fine to have a eventual consistency with respect to the user, but the application should be highly consistent when we are assigning a user to a particular driver, so that a particular driver is not assigned with multiple rides. Now, the next important non-functional requirement is the latency of the system. And whenever we are talking about the latency of the system with respect to the Uber and Ola, we are telling that once a user is asking or requesting for a ride, then our ride matching service should be able to assign a driver within a minute or so. So that is the latency that we are talking about. So here I will mention it that within a 1 minute time frame, a driver should get assigned to a particular ride request. Clear? And what will happen if we cannot assign a driver within a 1 minute interval? Then the request should fail. Means it should not load for an undefined period of time to find a nearest driver for a particular user. So that is what the latency talks about over here. These are more or less all the functional as well as the non-functional requirement that we have to keep in mind while designing this complete application. So since we are done with the functional and the non-functional requirement, that is the first step of our designing, let's go to the next step of our designing, and that is the identification of the code entity. And here if you look carefully, by reading the functional requirement of our system, you can easily identify that there are 4 to 5 code entities that we can easily find out over here. The first one is obviously the user or the rider. The next one is the driver. The third one is the fare that we are calculating based on the pickup and the drop location. Number 4, the ride, means the actual trip that we are doing. And number 5 is the location, means the pickup and the drop location of a particular ride. So these are more or less all the core entities that we can figure it out right now by reading this functional requirement that we have listed. So it might can happen that there will be few more core entities that you can figure it out while you will be designing the entire system. But as of now, just by reading the functional requirement, I think these 5 to 6 code entities are quite meaningful. Now let's go to the next step of our designing, and probably one of the crucial step of our system designing, and that is the API designing. So let's see what are the major REST endpoints that we have to expose over here to fulfill all the functional requirement that we have gathered. So let's move to the third step of our designing, and that is the API designing. And as I always tell you, designing an API endpoint is quite simple if you have done the functional requirement correctly, because in most of the cases, API designing has a one-to-one or one-to-many relationship with the functional requirement. So let's see all the list of API endpoints that we need over here. So as you have already understood, this system designing problem have primarily two actors. One is the driver and one is the user. So let's first see what are the endpoints that we have to create for the user, and after that we will be seeing that what are the endpoints that we need for the driver's end. So it is better to segregate both of them separately so that it will be very easy for you to explain to your interviewer. So the first thing that we will do is we will try to figure it out all the endpoints that we need for the user. So here if you look carefully, the first functional requirement, that is a rider should be able to get a fare estimation based on the start location and the start destination. Means we have to give an endpoint where the user can fetch the details, means the estimated fare of a particular ride based on the preferred location. And since here we are calculating something and getting some data from our backend, so obviously this will be a get endpoint. So let's see how the signature of this get endpoint will look like. So our first endpoint will look something like this. And what we are doing over here, we are calculating the fare of a particular ride. And for that, what we need a pickup latitude, the pickup longitude, the drop latitude and the drop longitude. So obviously a location is defined by a latitude and longitude. So here we have to pass the exact latitude and the longitude of a particular place so that we can calculate the fare accordingly. And the return type of this endpoint is the list of the fare with a particular request ID. So what does it mean? So here if you look carefully in our functional requirement, we have given the provision to our end user that he can book a particular ride based on the different vehicle types. Means it can be a bike or it can be a SUV or a car. So here we have to return all those fares in the form of a list. And for each and every fare, we have to give a request ID along with it. So it will be a request ID, the type of the vehicle and the estimated fare. So these three items should be present on a particular fare attribute. I hope this is clear. Now see what will be the next endpoint that we need to book a particular ride. So once the user gets an estimated fare on his front end, obviously the user would be requesting for that ride. So for that, what we have to do, we have to submit that request ID in our backend. And from where we are getting the request ID, we are getting the request ID from our first endpoint, that is this one. So here what we will do, in our second endpoint, we will make a post call to our backend with the request ID which the user want to opt for. So here what is happening, here we are sending the request ID in this API body, and once we send this request into our backend, what will happen, this will send a notification to all the drivers who are there nearby, and once a driver accept that particular request, this API endpoint should return a ride ID in the response. So here what we are doing, here we are returning a ride ID along with the driver details who is coming to pick the user. I hope this is clear. So here you can see that we have found out both the API endpoints that are required to book a particular ride. Let's now see what are the other endpoints that we need. So let me list down all those endpoints over here. So these are more or less all the endpoints that we need for the user. That is, so for example, the user want to check all the past histories of the ride he have done. So with the help of this endpoint, this will return all the rides that he have done in the past. Next, for example, a driver have already been assigned to a particular ride, but after that the user want to cancel that ride. And to support that, what we are doing, here we are having our next endpoint, that is canceling ride based on the ride ID. And the last one is provide the rating for a particular ride. So these are probably all the API endpoints that we need to fulfill all the functional requirement from the user aspect. Now let's go to the next phase, and that is designing all the API endpoint with the respect to the driver. So let me list down all those endpoints over here. After that, I will explain you in detail that what each and endpoint will do. So let's go through one by one. So here you can see the first endpoint that we need from the driver point of view is we need the exact location of the driver. And it is very much crucial to know the location of the driver rather than the user. Because at each and every moment, if we cannot track a driver, we cannot assign a ride to that driver. So it is very much needed that we get the exact location of the coordinate of each and every driver in near real time. And that is why what we are doing here, we are exposing our first endpoint, and that is the driver location, where we are getting the latitude and the longitude of our driver. And here if you look carefully, this is not an API endpoint, rather it is a WebSocket connection. Now why we need all these things, we will discuss it later. But as of now, just remember this point, that here to share the location of the driver, we are using a WebSocket connection and we are sending the latitude and the longitude. Now the next endpoint that is required is for the driver to accept or deny a particular request. So here if you look carefully on our second endpoint, we are telling that user is submitting a data, that is the request ID, means it is asking our backend service to find out the driver located nearby. And what our backend service is doing, taking this request ID, it is sending a notification, a push notification to all the nearby driver who are sitting idly. And once the driver gets that request, what he have to do, he either have to accept or decline the order. And once he accept or decline the order, what he is doing in return, he is sending the request ID with the confirmation or the acknowledgement message, means whether it is an accept or deny. And for that, what we need this endpoint. That is, here we are giving this endpoint. I hope this is clear. And the next two endpoints are the start and the end endpoint. Means once the driver picks up a particular user or the rider from the respective position, then he obviously have to start the ride. And to start the ride, he obviously need an API endpoint, and this is how the signature will look like. And once he drop the user to the final destination, he have to end that ride. And for that, this is the next endpoint that we are looking for. So here if you look carefully, these are more or less all the major endpoints that we need over here to fulfill all our functional requirements. There can be few more other endpoints that are required from the driver as well as from the user aspect. But if you have time during your interview, list down all the endpoints that you think that are useful. But remember, during your interview, you only have 45 minutes in hand, so probably listing all the endpoints would take a lot of time and you would not have enough time to design the actual application. Now, since we are done with the 3 steps of our designing, that is the gathering of the function and the non-functional requirement, the identification of the code entity and the API designing, now let's go into the next step of our designing, and that is the high level designing of our application, where we will try to identify all the core modules or the service that are needed to fulfill all our functional requirement and designing of our system. So let's go to the next part of our designing, and that is the high level designing. So let's start with the high level designing of this problem, where we will see all the major components or the major service that are needed to fulfill all the requirements that we have gathered. So here, if you look carefully, the first component or the first thing that we need is the few of the users who will be interacting with our application. So what I will do, I will draw a few of the users over here. So these are nothing but our users, and these are basically our mobile client from which user will be interacting. And here, if you see in our application, there are basically 2 types of user. One is the rider and another type of user are the drivers. So here we will consider one more type of actors in our system, that is nothing but our drivers. So here I will list down few of the drivers over here. Now, obviously, since here we are designing this system for a huge scale of audience, means here if you see, here we are scaling for millions of users and drivers. And obviously, that is why we have to go with the microservice architecture. And whenever we are talking about the distributed architecture, obviously, to handle the load, at that time we need a load balancer and the API gateway to route all our traffic accordingly. So what I will do, I will create a load balancer and the API gateway by which the user and the driver will be interacting with our backend services. So this will be nothing but a load balancer and a API gateway. And as you know, the functionality of the API gateway and the load balancer: number 1, authentication and authorization; number 2, routing of the traffic; number 3, rate limiting; and the last, distributing the traffic evenly across all our backend services. So these are all the roles and the responsibility of the API gateway and the load balancer. And here if you see, for distributing of traffic, what we are doing, we are using the round robin approach. So I hope this is clear and this is quite straightforward. So let's move to the next step, and that is the designing of the application. So here if you see on the functional requirement, the first service or the first component that we need is a service to calculate the fare estimation based on the location. So here what I will do, I will create a separate component or a separate service over here which will actually does the first thing, that is the fare calculation, means based on the traffic surge or whatever, it will return to the user an approximate figure. So this will be our first service called as a ride service. And how it will calculate? Based on the start and the drop location. So based on that 2 location parameter, means the latitude and the longitude of the pickup and the drop location, based on that it have to calculate an approximate fare. And obviously to calculate the distance between the 2 location and all those things, we will be using a third-party library that can be a Google map or a Apple map. Anything that is fine. So here will be one more service that will be a third-party service, which is nothing but a location map. And here we will be using a Google map or an Apple map. So let me write it down over here. I hope this flow is clear. So let's see how the flow is actually working. So here what is happening, once the user opens our application and put the pickup and the drop location to check the right fare, a request is first coming to our load balancer, and from our load balancer, based on the routing algorithm, the load balancer is directing the traffic to our ride service. And in this ride service, based on the pickup and the drop location, we are calling a third-party library or a third-party service that is nothing but a Google map. And based on that, it will obviously return the total effective kilometer between the pickup and the drop location. And based on that ETA and the total distance to travel, here in our ride service, we will basically calculate that fare. And once we get that estimation, we have to return it to our user. Clear? So all this mathematical calculation is done by this write service, and this location service is returning two things. One, distance between the drop and the pickup location, and the total time it takes for the traversal. So based on that, we are actually calculating the value over here. But on top of that, we also have to implement something more, that is the search charge and all these things, or the different type of fare estimation based on the vehicle type. So all those mathematical calculation and everything will be done by this write service. But we are not going into the detail of how we are doing it over here in the high level designing, because all those things will be covered in our last step of our designing, that is in the deep dive or in the low level designing. But as of now, we are just considering that here we are having our write service which is doing all this calculation. So once we give an estimation of the total amount of fare based on the ride location, obviously what the user will do, if he is fine with that estimation, he will book that cab. And as soon as the user accepts that fare, a request will come to our backend service using our API gateway, and it will go to the core of our application, and that is the driver matching service. So obviously right now it is just an estimated value or a quotation value, but right now we have to select a driver for that user who is located nearby. So here we will be having our next service called as the driver matching service. And what this driver matching service will do, it have to see all the list of the drivers available at a particular location. And based on that, it have to send the notification to all the drivers who are sitting idly that there is a ride that about to come. And based on that, if the driver accept that fare or the ride, then that notification will again go to the user that there is a confirmed driver who is coming. So to design that entire thing, what we need, here we need a driver DB where we have all the list of drivers that are present in our database. And this driver matching service will scan this list of drivers which are present near to that particular location. And once this driver matching service gets a list of all the drivers that are near to that location, it have to send the notification to that driver. And for that, what we have to do, we need a notification service over here. So this will be our notification service. And obviously if the user is using an Android application, then the notification service is nothing but a FCM, means the Firebase cloud messaging. And if he is using an iOS device, then it will be a Apple push notification. So based on the device OS, we are choosing the notification service accordingly. Clear? So here from this driver service, a notification will go to all the drivers that are present near to that location. So here we will be just showing it like this. And once the driver accept that request or deny a request, an acknowledgement will come to our backend service using the same load balancer. So from here, our accept or a deny notification will come, and it will again come into our driver matching service. That is the request that you have sent to the driver that has been accepted by the driver. And thus now the request that we have sent will now get converted into a ride. So what we need, from here we need to insert it into a separate database, and that is a ride database. So here we will be having a ride DB which will have the complete information of the booking. Means a ride have been booked from point A to the point B, what is the estimated fare for that ride, who will be the driver to pick up that ride, and all this information we will capture in this ride DB. Clear? Now once the ride have been completed by the driver, there we have to do two things. Number one, we have to accept the payment from the user, and number two, that is the optional one, that is the user and the driver can provide a rating to that ride. And for that we need two services over here. So the first service that we will be listing over here is the rating service. So here we are having our next service called as the rating service. And as the name suggests, this service is completely responsible to provide the rating to the user as well as to the driver. And obviously this need a database to persist all the ratings of the driver as well as the user, so that in the future we can show that what is the rating for a particular driver who is coming to pick you up. So to implement that feature, what we need, here we need one more database called as a rating DB. And the next thing that we have to do is the payment service. And for that there will be one more service called as a simple payment service, which will accept all the payments that we are taking from the user. So this will also go through our load balancer, and obviously we need to persist all the payment related information, and for that we are having another database or another table called as our payment table. I hope the entire flow is clear. So what is happening on the first step, we are checking the fare calculation, means what can be an approximate fare for a particular ride, and once the user is satisfied with the price, he will confirm that booking, and for that the request will come to a driver matching service, and this driver matching service will look for all the drivers that are present nearby, and based on that it will send a notification, a push notification to all the drivers over there. And once a driver accepts that order, a simple acknowledgement will come to this driver matching service, and thus that request will get converted into a proper ride. And thus we are inserting into our ride database, and here also we are sending a notification to all our users that your ride got accepted and a driver is on their way. And once this entire ride process is done and we are complete with the ride, then what we are doing, we are accepting the payment from the user, and we are giving the option for the user to give the rating for that particular ride. I hope this is clear. Now if you look carefully, there is one more small component that is missing. That is, here if you see, we want to do real-time tracking of the user as well as the driver. And to implement that functionality, what we need one more service that will update or track the location of the driver periodically. And for that, what we need one more service called as the location update service. And as the name suggests, it is quite simple. That is, it will take the location from the user as well as from the driver, and obviously it have to update this driver database that we have over here, so that the driver matching service can track all the drivers in the near real time and can allocate the ride accordingly. So this service will basically update this location attribute for this driver database. So here if you look carefully, we have almost covered all the major functional requirements that we have listed over here, starting from the fare calculation, acceptance and the decline of the request, pickup, real-time tracking and everything that are possible over here on the functional requirement. But the things are not at all simple the way it looks like, because here this ride matching service have to do a lot of job to find a particular driver on a particular location, because obviously there will be millions and millions of drivers that are present in our entire database. So it is not possible to scan through all this driver list to find a particular driver. So there are a lot of optimization and things that are still missing on this architecture or in this designing that we will be seeing in our next phase of our designing. That is the last and the final step, and that is the low level or the deep dive analysis of our high level designing, where we will break down each and every component in detail, and we will see how each and every component will interact with each other and how we can optimize it even further. So without wasting much time, let's go to the last and the final step of our designing, and that is the deep dive or the low level designing of this problem. Before proceeding further, I just wanted to notify that I have created a very simple website over here so that you get all the contents that I upload on the YouTube on a single platform. So here you can see there are lots of content on the system designing, on the low level system designing. Similarly, here we have the complete graph playlist where we have already 15 to 16 video over here, as well as all the latest contents that I'm uploading on the YouTube. I will keep on updating all those things in this website. This is a free website that is hosted also in a free domain. So do not forget to bookmark this website so that it will be helpful for you to find out all the relevant contents regarding your upcoming interview. So let's start with our low level designing, and the first thing that I will do, I will copy this entire designing and I will paste it into our low level section so that we can enhance this design even further. So let's start with our first component, and that is our ride service, where we are doing the fare calculation or the fare estimation based on the pickup and the drop location. So what this ride service is doing, so as soon as a user is looking for an estimated fare for a particular ride, this ride service will internally send another request to our Google Map service to find out the roadmap and the traffic for that particular ride. So based on the pickup and the drop location, this Google Map service will return two things. Number one, the route or the distance between the 2 point, and number two, the ETA for that ride. And based on that, this ride service is actually doing the calculation. And how it will do? It is quite simple. So for example, you want to travel via bike and you want to take the estimation for the bike service. And let's take an example that the rate of the bike is 20 rupees per kilometer. Similarly, for a car, the rate is 60 rupees per kilometer. And based on this configured value that are predefined into our server or into our database, this ride service have to calculate the final value. So here what we need another database that is nothing but a fare or a rate database. So here I will keep one more database called as the rate or the fare database, which will consist of all the information about the rate of a particular vehicle. So here all this information will be residing on this database. Also for this bike, the waiting charge can be 1 rupees per minute, and all this information should be present within this rate database for all type of vehicles that are present or we support in our application. And based on this calculation or the metadata that we have here, this ride service will do a computation over here. So the time and the distance this Google Map is sharing, it will simply multiply it with this value that is present over here, and based on that it will give a approx estimation of the fare, and this will get returned to the user. I hope this is clear. But there can be also a follow-up question, that is, obviously this rate cannot be a fixed rate, because if you know, whenever there is a high traffic or a high request for a ride, there is a surge price that is associated in Uber and Ola. And how that is done? That can be easily done with the help of some analytics. So what we will do here, all this request for the ride, though it is not required for us to save in the database, but we will save it into a database for some analytics. So here we will be having one more DB called as the ride request DB. And this will completely be used for the analytical purpose and for the calculation of the search price. So what actually happens is, like, if you see, whenever we try to request for a ride from a location A to a location B for multiple number of times, you can see the price will keep on increasing with time, because the system identifies that there are a lot of demand of the cab on those two locations, and based on that it adds a surge price into its base fare. And here if you look carefully, the ride service, what it is doing here by the computation of these two is actually calculating the base fare. But if there is a search thing, means if more number of requests are coming into our database, then we have to multiply that base price with some 1x, 2x or 3x. And to implement that feature, what we do, all the requests that are coming from the user, we will persist it into our ride request database. And from this ride request database, there will be one more service, that is a search calculator service. And this search calculator service, what it will do, it will read from the ride request database and it will return a multiplier to this ride service. So here what happens, this ride service will request this search calculator service to return a particular integer or a particular search value. And how this is getting calculated? Based on some analytical approach, this search calculator service will read all the data from this ride request service, and based on that it will return a 1.5, 1.3, all this search value to this ride service. And after that, after multiplying all those things, whatever the data or whatever the final value that comes for a particular ride, that will go as a response to the user for this particular request. I hope this is completely clear that how we are giving a particular fare estimation for our ride. Clear? Now, once the user is fine with this estimated value of the ride, what he will do, he will try to book that ride. And for that, our request will be coming to our driver matching service, where all the computation of finding a driver will happen. So I need a lot of space to elaborate this mechanism of how we will be designing the driver matching service, and let's see how this service will actually work. So the main logic by which this driver matching service will actually work is with the help of the proximity search algorithm, which I have explained in detail in my 7th video on this playlist. So if you are not familiar with what is a proximity search algorithm, I would request you to go through that video first and then come back to this video, because without understanding that proximity search, here it is impossible to understand that how this driver matching service will identify the driver on a particular location. So with the assumption that you have already gone through my 7th video, that is the proximity search algorithm, let's proceed further. So here the driver matching service will find out all the drivers from the nearby location with the help of the geohashing technique, where we represent a particular location with alphanumeric character, and based on that we locate a particular attribute on the globe. And here also, with the help of that geo proximity search, we will be finding a particular driver for a user. So here, once the user try to make a booking, the request will come into our driver matching service with the pickup location of the user. And by looking at the pickup location of the user, a geo proximity search algorithm will work across this driver database, which is obviously sharded by location. And based on this algorithm, it will list down all the drivers that are present in a 5 km or a 10 km radius for a particular user. So let's first see how this driver database will look like. So this driver database is very simple. It only consists of all the metadata of the driver. And since here we are just considering all the metadata, that is why we will consider a Postgres database. And let's see what are the attributes that we have to store in this database. So these are more or less all the attributes that we need for a driver database. So here we are having the driver ID, the name of the driver, the vehicle information, the rating, mobile number, the status of the driver, means whether he's sitting idly or he is driving or whatsoever, and all the other metadata of a particular driver. And along with this information, we also need the location of the driver. And for that also, we will be having one more table called as a location table, which will consist of the latitude and the longitude of both the driver as well as user, which we will be updating periodically. So let's see how the schema structure will look like. After that, I will let you know how we will update it on the real time. So this is how our location database will look like. So here we are having a driver ID or a user ID. So you can use this table for both the user as well as for the driver. After that, we have the latitude, the longitude, and the modified timestamp. Now let's take an assumption that all the drivers somehow are updating their location periodically into this driver database. Now with this assumption, what is happening? All the data that are present over here are near real time. And with that assumption, what we will do? Here, this driver matching service will pull all the drivers that are present to a particular location. Now let's take an example that here for a location, we got the list of all the 5 drivers that are present near to the user. So here we have all the list, that is driver 1, driver 2, and so on. So here we have this complete list of drivers who are present on that location. Now what we have to do? We have to send notification to each and every driver that are present. So for that, what we are doing? We are using this notification service. That is fine. But there is a small problem over here. That is, since this is a microservice architecture and there will be a lot of concurrent services that are running on different pods, it can happen that 2 users are present at a particular location. That is quite a real case, right? And for both the requests, we got all the list of same driver in the response, because the pickup point is same for both the requests and all the list of ideal driver is also same. So what will happen with this architecture is like both the server 1 and the server 2 will send the request to the same driver at the same time. And it can happen that the driver accept both of them. Then there will be a problem with the consistency of the driver matching service. Means the single driver will get mapped to 2 different rides at the same time. So we have to omit this consistency issue over here, because that is a crucial non-functional requirement that we have listed over here, that our system should be highly consistent in the ride matching service to prevent any driver from being accepted by multiple rides simultaneously. So to implement this feature or to design this feature, we need the help of a locking system while assigning a driver for a particular ride. So if you have already watched my 6th video where I was designing the driver matching services for Zomato application, there you must be remembering that I was using a Redis log over there to solve this use case. And here also with the help of the Redis log, you can also achieve the same thing. That is, once you are sending a request to a particular driver, you keep this driver in a Redis log, which is actually a global log, and you just send the notification. And until and unless the driver does not acknowledge that request or it does not timed out, you should keep that log as it is in your Redis cache so that no other service can send the request to the same driver until the log is over. So with that approach also, we can solve the same problem over here. But here I will do it a bit differently. That is, rather than using a Redis cluster, what we will be doing, we will be using a Zookeeper over here to achieve that locking mechanism. So let's understand that how with the help of the Zookeeper, we will achieve this locking mechanism over here, and we can design a consistent system so that we do not send multiple drive requests at the same time to a single driver. So let's see how it will work. So if you have remembered my first video on system designing where we were designing the URL shortening app, there I have used a Zookeeper approach to solve that problem. Now if you have gone through that video, there I have explained you in detail that what is a Zookeeper, how does it work and all those things. So let me just go through that point one more time so that it will be very easy for you to understand. So here if you just consider the first system designing video on my channel, that is when I was designing the tiny URL, there I have mentioned about the Zookeeper. So what a Zookeeper does? So a Zookeeper is a distributed open source coordinating service for distributed application, providing a centralized service for configuration management, naming, synchronization, and all those things. So here if you just go through this section of the Zookeeper, you will get to know that how the internal things of the Zookeeper actually works. But just for a recap, I want to tell you that Zookeeper have two types of node in their system. One is called the persistent node and another is known as the ephemeral node. And the persistent node is the node that cannot be deleted from the Zookeeper, and the ephemeral node can be deleted based on the requirement. So these are the two type of nodes that are present within the Zookeeper. Now let's see with the help of this concept how we will create the lock within a Zookeeper. So what will happen? Let's take an example. This is the persistent node of the Zookeeper, and here we want to create the driver log. So what will happen is like, obviously, since this is a microservice and we need a huge scaling of this service, so there will be lot of instances of this driver matching service. And once this driver matching service want to hold a particular lock on a driver for sending the notification, what it will do? It will simply create a lock in the Zookeeper. And creating a lock in the Zookeeper means you are creating a ephemeral node within the Zookeeper. So for example, the first server of our driver matching service want to create a log on the driver one. So it will create a ephemeral node, and the value that it will persist over here is nothing but the driver ID. Means the server one is creating a log on the driver ID 001. Clear? Now, for example, the next server, that is the server 2, also want to create a log on the driver 1. What will happen? This Zookeeper will not allow to create another ephemeral node over here. So what it will do? It will throw an exception while creating the ephemeral node. And the exception will be node already exists. Means there is already a log that is present in the Zookeeper. So you cannot or you should not send the same notification. Means you should not send the notification of a write to that driver. And once the first service is done with the log, means he have sent the notification to the driver 1, then there is a request for the write, and in case the driver 1 doesn't respond within the time frame or he denied that write, what will happen? The server 1 will release the log from the driver 1. So what will do? It will delete this ephemeral node from the Zookeeper. And thus, once it deletes the ephemeral node, the second server who is also want to send a notification on the same region for driver 1 now can send the notification to him because the log has been released. So whenever a particular server wants to create a lock on a driver, it have to create a ephemeral node in the Zookeeper. And if the second service also want to hold that same lock, at that time it will get an exception because the ephemeral node has already been created by other service, means the lock is already been created. Now the question might arise like, for example, the service 1 have created a particular lock over here, and thereafter creating the lock, that server dies or it got crashed. Now what will happen to that lock? Will it remain forever? No. What happens in the Zookeeper is like, with the help of the lively node or the actuator, this Zookeeper always track the existence of the server who have created the lock. So if the service who have created the lock dies or crash in between, then this lock or then this node will get automatically deleted from the Zookeeper, and thus the lock will be released from the Zookeeper, and all other subsequent server can send the request or hold the lock for the driver. I hope this is clear that how with the help of the Zookeeper we are establishing the fact that no driver gets two write requests from two different users at the same time. I hope this is clear. Let me write all these things over here regarding the Zookeeper so that it will be easy for you to understand that how we are implementing the lock with the help of the Zookeeper. So here if you read this thing carefully, you will get to know that how the lock will happen with the help of the Zookeeper and all those things which I have explained you right now. So feel free to go through all this documentation in my website. So this is how we will achieve the consistency in our system. Now let's go to the main thing. That is, here, while we were designing this system, we have taken an assumption that this driver database consists of all the real-time location of the driver, which is actually not possible in the real world. So let's see how we will get the real-time update from the driver, and based on that, how we will write all our logics. So what happens in the real world while designing this type of system? To get a continuous location update from the driver as well as from the user, what we need a WebSocket connection. So obviously you know that what is the difference between an HTTP request and the WebSocket connection. So the difference is like, the HTTP request is a single directional request, whereas a WebSocket connection is a bidirectional duplex connection, where it is possible to send the data from the client to the server. Similarly, it is possible to send the data from the server to the client. So it is basically a duplex connection where you can transfer the data at any moment. And here to send the real-time update location of the driver, we need a WebSocket connection, because otherwise to send the driver location in the near real time to our backend service, what we have to do, we have to send the geographical location of the driver each and every 5 to 10 seconds to our backend server, which is actually not a feasible solution, because you can easily understand that the scale which we have considered over here is the millions of the users and the driver. And if you consider that millions of user or the driver are hitting our backend on each and every 10 seconds, so you can easily identify that, or you can easily estimate that the total number of requests to update the location from the driver and the user will be in billions, and it is not possible for our backend service to handle that amount of load in the real world. So to do that feature and to get the real-time update of the driver, what we have to do, we have to go for the WebSocket connection. I hope you got the idea that why we need a WebSocket connection to update the driver and the user location. And as I have already told you, if your application is WebSocket heavy, it is better to use a separate load balancer that is dedicated only for a WebSocket connection rather than using the same HTTP load balancer here. Though all the modern load balancer and the API gateway support both the HTTP as well as the WebSocket connection, but it is better to have a dedicated load balancer for the WebSocket connection, because in case of the WebSocket connection, also you have to remember we have to handle the stickiness of the connection. Means if the server 1 is connected to the client 1, then throughout the journey of the driver, that same server should get connected to the same client. So to handle that stickiness, we need a dedicated WebSocket gateway. And for that, what I will do, here I will create one more WebSocket gateway that will look something like this. And the responsibility of this gateway will be also same, that is authentication and authorization and the session stickiness. So let me write down all those things over here. So what is happening over here? Since these are all the WebSocket connection, all the drivers who are right now active in our system are currently sending their real-time updates on the geographical location into our backend. And with the help of the WebSocket connection and the WebSocket gateway, all these requests are going into our WebSocket server, which is nothing but our location update service. So here we will be having one more service called as a location update service, which is a WebSocket server. I hope this is clear. So all the real-time updates of the driver are right now stored in this WebSocket server. Now, here if you remember, when I was explaining you the driver matching service, I had made the assumption that all the location of the driver that we have in this database are in near real time. But that is actually not true, because here if you understand, we are getting millions and millions of data in our WebSocket server in near real time, and maybe on each and every 5 seconds location of the driver is getting changed. And on that same rate, if we keep on updating this driver database to update this location value, then it is obviously a very bad approach of designing, because it is not possible for the database to update with that huge amount of the throughput. So what we will do, instead of directly updating this location and the latitude of our database, here we will introduce a Redis cache to store the information of the driver. So what will happen? Here we will introduce a Redis cache to update all the driver locations. So this will be our Redis cache, and this will have all the geographical location of the driver who are currently active. So for example, there are some of the driver who are right now not doing duty. So we will not store those location here. Rather, only those driver who are currently active and serving their duty, only the location of those active driver we will persist it in this Redis cache. And as you understood, since those drivers are active and our location are there in the Redis cache, now what we can do, this driver matching service will actually call this Redis cache to get the matching driver to find a particular ride. Clear? So let me tell you the entire flow one more time so that it will be very easy for you to understand and imagine how the complete data flow of this designing is actually working. So what will happen is, like, first the user will make a request into our backend service to get an estimation of the fare. For that we have this ride service which is actually calculating the fare. Clear? Now once the fare is returned to the user will be opting for a ride, and once the user accepts that fare, the request will come to this driver matching service, that right now we need to find a nearby driver for that user. And to find the nearby driver, what we need to do here, instead of searching this database, what we are doing, we are searching all the active driver within this Redis cache. And since this Redis is a cache, so obviously the scan time or the fetch time will be pretty nominal. So from here, let's take an example that for a particular location of the user, we got 5 drivers in that location who are sitting idly and waiting for their ride. So what we will do here, we will initiate our Zookeeper. So there will be one more service over here that we have already discussed. That is, here we will be having our Zookeeper service. And what this driver matching service will do right now, it will keep an iterator service over all the driver who are currently active and waiting for their next ride. So it will first pick up the driver one, it will first create a log on this Zookeeper, and it will simply send a notification to the driver one. So with the help of the notification service, the request will go over here to the driver that we got a user near to you which you have to pick up. So if the driver accept the request, the notification will come to our API gateway, and from there the acknowledgement will come to our driver matching service. And once we get the acknowledgement from the driver, what we will do, we will get the complete information of the driver from this driver database, and we will send the same notification to the driver as well as the user. That is, this is the place from where user should be picked up, and also the location of the driver to the user. So here, with the help of the open WebSocket connection, we will send all these messages to both the user as well as the driver. Clear? Now on the flip side, if the driver 1 doesn't accept the order or he intentionally clicks or deny, same thing will happen. That is, the request will go to our API gateway. From there, it will go to the driver matching service, and thus here, since the driver have not accepted the request, so first what we will do, we will release the log from the Zookeeper for the driver 1, and thereafter we will scan the next driver, that is the driver 2, and again in the same way we will send the notification to the driver 2 via this path, and the same thing will happen again. So I hope you are clear with that how with the help of this mechanism we are sending the notification to the driver as well as the client, and we are updating everything in near real time with the help of the WebSocket connection. Now let me write all these things in the arrow mark so that it will be very easy for you to understand in the future. So here if you look carefully, I have mentioned everything that I have explained. So here the driver and the user are updating their location in every 5 to 10 seconds. Number 2, we are sending the notification to all the drivers and putting it in the Redis or in the Zookeeper to create a log. And here also remember that there can be thousands and thousands of drivers that are present on a particular location where the user is. So to get an optimal solution, we try to find out the top key drivers that are present near to that location. So it can be top 5 or top 10, because if you remember, here we have also considered one thing, that the latency of this application should be 1 minute. Means we should either find a driver or we should time out within the 1 minute time frame. So to achieve this point, what we have to do here, we have to make top 5 or a top 10 select from the driver list. Because if you just make a calculation, so for example, we are sending the notification to driver 1, and after a 10-second window, obviously that notification will get timed off. So on the worst case, a particular driver is taking 10 seconds to either acknowledge or deny. So it is possible that we can only make request to 5 to 6 driver for a particular write request, because 6 into 10 is equal to 60 seconds. That means the 1 minute. And obviously we have to consider the time to travel for this request. So obviously we cannot have more than 5 requests for a particular write. So here it is better that the value of the k will be 5. I hope you got the idea that why we are doing this logic and how we are achieving this non-functional requirement. I hope this is clear. And also here, if you look carefully, I have also mentioned that if there is a timeout for the driver, means a driver didn't respond within the 10-second window, then we have to simply delete that node from the Zookeeper and we will unlock the driver. Clear? So here, if you look carefully, we have almost solved everything of how to assign a driver for a particular user. Now let's see something different. That is, once the write have been completed, how we will perform the payment and how we will give the rating to the driver as well as to the user. So for that, the flow is quite simple. So for the rating service, here we will be having one more service called as a rating service. So this will be one more service, that is our rating service. And all the requests for the rating, means whether it is a user rating or the driver rating, will first come to our rating service. And from here, we will be persisting it in our rating database, which we have already made it over here. So here we are having our rating table or our rating database. So let me show you how the schema structure of the rating database will look like. So this is how our rating database will look like. So it is simply a Postgres database, and here we are having the sender ID, the receiver ID, the rating timestamp, and the write ID for which we are providing the rating. Clear? So the sender ID can be a driver ID or the user ID. Similarly, the receiver ID can be a driver ID or a user ID. So this will be the schema structure of the rating database. And once the drive or the write is completed, the user have to do the payment. And for that also, we will be having a simple flow, and that is we will be having a payment service over here. So here we will be having our payment service, and as I've already shown you in my previous video, that is a payment service have to call a third-party service, that is a payment gateway service. And once the payment is done successfully or failed from our third-party service, what we have to do, we have to update the payment database, which is nothing but a MySQL or a Postgres database, because a payment related information should be highly consistent and it should have the ACID property. So we have to go with an RDBMS solution. So I'm not designing the payment service over here because I have shown it in all my previous video. So I am skipping it right now. Clear? But here if you look carefully, we are having a write database, and obviously this write database will have a lot of table and lot of metadata that it have to persist. So let's see what are the schemas or what are the tables that should be there within this write database. So here if you look carefully, we need primarily two tables within our write DB. Number one is the estimated fare and number two is the write table. Let me just explain you what each and every table will do. So what happens is, like, once the user do a fare calculation using our write service, what will happen is, like, this will return all the calculation to the user. And once the user is fine with that estimation, obviously it will send a write request to this driver matching service. And once he send that request into our backend, means within our driver matching service, we first have to persist that request information into our write database. And where we are persisting it? We are persisting it in our estimated fare. And here what we are doing? Here we are having the request ID, means the request for which the user have accepted the fare, the pickup location, the drop location, the fare for which he have accepted, the currency, timestamp, vehicle type, and the user ID. So these are nothing but all the metadata of the request ID for which the fare has been accepted by the user. Clear? Now once the fare has been accepted and everything is persisted in our database, what will happen? This service will look for the driver, which we have described over here. And as soon as it have found out a driver who have accepted the write, it will update this write table. And here what we are having? Here we are having a write ID, which is nothing but the request ID that we have saved over here. After that, we are having the user ID, the driver ID who got allocated for this corresponding write ID. After that, we have the source location, the driver location, and the status. And the status can be anything, means the driver has been allocated, he is coming, he is on ride, reach the destination. So all those things will be the status of the write service. So I hope this is clear that how we are saving all this metadata in our backend. Now there can be a question that why we need to save all this information of the fare over here. And the reason behind saving the estimated fare over here is because if you know, when we are using our Uber or the Ola app, here when we book a service, there we get an estimated ride. And after the completion of the ride, sometimes it happens that based on the traffic or based on the route change while traveling, the fare can differ between the estimated fare and the actual fare. And to keep the track of both of them, here we are having both the estimated fare over here and the actual fare in the payment database in the payment service. So that in the future, if the user opts for a return, then at that time we can process the return based on some calculation. And that is why we have to persist both the estimated fare as well as actual fare in our database. I hope this is clear that how we are saving all this information in our backend service. Now there is one small point that we also have to save over here, that is for calculating this cashback. Means, for example, there is a change in the actual fare and the estimated fare, and to calculate that whether the actual fare is actually meaningful or not and why there's a difference of the fare, obviously we need some metadata to compute that. And what we need the complete track of the route by which the driver have completed this entire ride. And for that, what we need here, we need one more database or one more service to track a particular driver when he's actually on ride. So what we will do here, from this location database, we will be having one more service, and that is nothing but a simple queue. Means all the update of the location that are coming into our WebSocket server for all the driver who are actually in ride, for them what we are doing, here we are having a separate queue or a Kafka service. And from this Kafka service, there will be a consumer service fulfilling a PubSub architecture who will be reconciling all this data periodically in our backend so that we get enough information when a particular ride is actually happening. So let me write down all these things. After that, it will be very easy for you to understand that what we are actually trying to achieve. So here if you see, we are having a Kafka queue, which are having all the location of the driver who are actually on drive. And here we are having a trip consumer service. And what it actually does, it periodically updates the driver location status and the rating of the driver and also the route by which the driver have made the ride, so that it will be easy for us to do a refund calculation if the user is opting for. So I hope you are clear with how we are doing all these things. And here if you look carefully, there is a small gap in this database. That is, here we are having a rating database. Similarly, over here also in the driver, we are also having rating over here. So this can create a duplicate or an inconsistency in our service. So basically what we have to do, here we may have to write some reconciliation job to update all this rating from this database and update the driver rating over here. So here in this table, we are having all the granular update of the rating, means which user have given which rating. And similarly, this service is nothing but an aggregator job which will combine all the ratings together, will make an average out of it, and it will simply update the rating for a particular driver. So this is nothing but a simple aggregator service which is taking the data from this database and it will update the rating of the driver DB. So here if you look carefully, we have covered almost everything that is possible to design for a ride sharing service like Uber or Ola. And here if you look carefully, we have not only solved all the functional requirements that we have gathered over here, but also we have fulfilled all the non-functional requirements that we have gathered. So I hope you have thoroughly understood this video and you have found this video useful. And if you have found this video useful, do not forget to like, share and subscribe to my channel and hit the bell icon so that you never miss an update from my channel and you are always ready for your next interview. So see you on our next video where we will be solving another problem statement from the system designing interview. So see you on our next video. Thank you.